scan the QR code. And if you guys are happy for just send it. But yeah, if you're happy to, make sure to scan the QR code. And we can start with introductions. So how it's going to go is for like 10-15 minutes, I will do moderating questions. So I will ask you guys things specific to your career, your research, and then I'll open the floor for open Q&A, and then everyone can ask questions. So yeah, first let's get introductions out of the way. So first up we have Dr. Brian Keating. So feel free to introduce yourself.
Oh, introduce myself. Okay, that's dangerous. Yeah, someone introduced me. It was ridiculous. I gave a speech in LA at the Museum of Tolerance on Sunday, and the person that introduced me, I was embarrassed. I felt like I want to know that person because he sounds really cool. And I asked, did you talk to my mother to get the introduction? Because it was just, you should have gotten a rebuttal. I can do the rebuttal tonight. Anything sounds good. So Brian Keating, been at UCSD since 2004. So maybe some of you weren't even born in 2000. Maybe all of you weren't.
I was not born.
You were not born, okay. That's okay. So came here then. I study the oldest light in the universe, the cosmic microwave background radiation. We build telescopes that we put in really cool places like the South Pole, Antarctica, I've been there twice, and the high altitude desert of Chile called the Atacama Desert, 17,500 feet above sea level. We build the biggest, largest instrumentation ever built, largest numbers of detectors, most sensitive instruments, 400 people around the world working on this project to get information on what put the bang in the Big Bang. We know something like the Big Bang occurred. We know something very different from our conditions now existed when the universe first came into existence, but we don't know how it came into existence. We don't know what the infant universe was really like, so we try to take pictures, baby pictures of the universe, but you can't do that with light. You have to use microwaves, radio frequency waves, shorter frequency than normal, lower frequency than radio waves, and we use those to uncover the properties of what the universe, the space, the time, the matter, the energy, the density, pressure, temperature, all the physical features that you go and see a doctor. If you were an infant, you take your baby to the doctor and they say, well, how much does it weigh? How big is it? How fast is it going to expand? And we revealed a lot of different features about the universe that have put a lot of questions in our minds. And I always say that the flaws in something lead to new laws. When you learn something that doesn't fit in, most people think scientists, oh, eureka, I found it, I knew I was going to find it. And that's not the way science happens. Almost never. I mean, maybe these guys are better than scientists than I am, but that almost never happens. And when it does, you need to be really careful that you didn't make a mistake. So one of the ways you can trick yourself into fooling yourself that you discovered what you wanted to see is called confirmation bias. It's very dangerous. So we guard against that. And one of the things that can mimic the signals that we're looking for turns out to be astrophysical, but not cosmological. In other words, there's something in our galaxy produced by a star that can actually produce the exact signals that we're looking for and mimic those, causing us to make a false claim of detection of the birth of the universe, which we did in 2014, and we had to retract it. It's one of the biggest kind of oopsies in modern science. But luckily we've recovered from that, moved on, built bigger and better things. But interestingly, the source of the signal that fooled us, tricked us into believing what we thought we see was the infant universe being born, are actually meteorites. Microscopic grains of metal and dust and rock and space from a preceding star in our galaxy that blew up and scattered its ashes throughout the cosmos. In particular, it can get aligned with the magnetic field of the Milky Way. So I've actually, as a kind of a, maybe it's an offering, like to a spirit, to something to prevent that tricks from happening and only have treats. I brought some meteorites for you guys to get, and panelists too can learn too. So some meteorites, and to get one, you just have to sign up on this QR code up here. So I'll be checking, make sure you did it. Everyone gets a meteorite. They're 4.3 billion years old, found in Argentina, and you get some cool facts about the meteors. They're slightly radioactive, so be careful, but no more so than a banana or than dinner that they should provide. So come up afterwards, after we're done kind of blabbing, and then give your meteorite.
Next up, we have Dr. Burgasser.
Hello, everyone. evening. My name's Burgasser, pronouns are he, him. I've been a professor here since 2010, but before that I was actually an undergraduate here at UCSD in New York College in the 20th century. So definitely before I think most of you were born. And I was a physics major here. I went off to go get a PhD at Caltech up in Pasadena. The usual path is that we go on to do a couple postdoc positions, and then after a short period of being a professor at MIT, I came back here in 2010 and I've been here ever since. I am an observational astronomer, just like Brian, but I look in a different part of the electromagnetic spectrum. I look more at the optical and then infrared wavelengths in the night sky, so just kind of red of what we can see with our eyes. And I do that because the objects I study are very cool stars and extrasolar planets, and then things that are kind of in between called brown dwarfs, which we like to call failed stars, which sounds terrible. But that's what they are. They are stars that don't fuse hydrogen in their cores, and as a result, they just shrink down to about the size of Jupiter, and they are floating around all over the place. And we didn't know any of these things existed prior to about 1995, so about 30 years ago. And now we know tens of thousands of these objects, and we're finding more every day. They're very, very common, but they're just very dim. So I'm part of the new astronomy and astrophysics department. I teach classes all the way from kind of lower division courses that are kind of general courses on both astronomy, but also in the DEI course sequence. And then we also teach upper division courses, graduate courses, seminars. We all have kind of different kind of areas that we teach in, and often kind of different over the course of the year. I don't think anybody else said that.
We can also talk your fun fact. I included that
Yeah.
you are in the UCSD Athletics Hall of Fame for diving.
Yeah, if you go over to REMAC, you can find a tiny little picture of me. I'm not wearing many clothes in it because I was a diving athlete. I don't look like that anymore. But yeah, when I was an undergraduate here, I did athletics for the 4 years I was here and had a great career. And now my body does not work that way anymore, but it was fun while it lasted.
Your brain still does, though.
My brain still works. Actually, I think my brain works better than it does. So that's good. Yeah.
And up next, we have Dr. Ethan Nadler.
All right, hi everyone, I'm Ethan Nadler. So I joined the, as Adam mentioned, new Astronomy and Astrophysics department about 1 year ago as an assistant professor. So one of the really exciting things of building that new department was they hired new young faculty, and I was really lucky to be one of those people. So I have kind of bounced around California throughout my academic journey. So I did my undergrad at UC Santa Barbara, went up to Stanford for grad school. I was in LA as a postdoc, and then finally ended up in San Diego. And I'm a theorist and a simulator, so I'm basically trying to figure out what the universe is made of. And one of the really fascinating things that we've learned from astrophysics and cosmology is that we don't know the answer to that question. So all the types of matter and energy that we're familiar with on Earth make up a very small portion of everything that's out there in the universe. In particular, there's something called dark matter. We don't know what it is, but it's some substance that gravitates, and if we could figure out what it is, we would definitely learn really important new fundamental physics. And there's also something else called dark energy, which, for example, Brian studies. So I'm mostly focused on dark matter. I'm trying to figure out what is the stuff that makes up the universe. And there's two ways to do that. One way that's really useful is to look at the properties of galaxies. And so this is why I'm in an astrophysics department, not a physics department, because galaxies have been forever like our only real positive source of evidence for dark matter until much later the cosmic microwave background came. And kind of the idea is that galaxies form inside of clumps of dark matter, essentially balls of dark matter. We call those objects dark matter halos. And so one thing that really captured me when I was learning about this subject was that if there's no dark matter, then essentially galaxies never really form. Like we wouldn't be here to ask the question of what dark matter is. And I found that really kind of profound, and it still really bothers me to this day that we don't know what this stuff is. So I'm working very hard on it, trying to run simulations to mimic how our universe looks in different scenarios for what the dark matter might be, and then compare those to the data. And the other way, which I'll just briefly mention, is using this idea called gravitational lensing, which is just the fact that massive objects, the gravitational field of those objects bends light. So if we have some light coming at us from a distant place in the universe, the path of that light is bent. And the amount of bending depends on how much mass it's passing through. So So we can use that essentially to infer like the structure of mass that's out there in the universe. So these are things I like to think about. I'm happy to talk about it more. I can't remember what my fun fact is. Oh yes, so I got into physics, I don't know, I feel kind of late actually. So for a long time I guess I was also trying to be an athlete or was an athlete. I thought I don't know, spend my life playing tennis or something like that. And it wasn't until I went to community college fairly late that I got into math and physics, and then I was lucky to be in this really awesome undergrad program in Santa Barbara. So that's what kickstarted my interest.
And next up, our last introduction we have is Dr. Julie Inglis.
Hi. So I've only been a doctor for about a month and a half, so I've done a little bit less than the rest of the panel here. But I did my undergrad in Canada, and I kind of took a circuitous route to get to physics. I started off in biology and then transitioned into material sciences for a while where I worked on lithium-ion batteries, and then eventually I stopped being in denial that I wanted to be an astronomer, and I was lucky enough to get into Caltech to do my PhD in planetary science, where I looked at exoplanet atmospheres. And basically, I ended up studying for a few years. It would take Jupiter in our solar system and move it into very strange places, so either very, very far away from its host star or very, very close in, so it heats up to a few thousand degrees where you really wouldn't want to be in the atmosphere. Those are the types of objects that I studied during my graduate school degree. And they have some very neat properties because of their extreme environments. Some of them smell like rotten eggs because they have hydrogen sulfide in their atmosphere. Some of them rain rocks down because they're so hot that the only condensates that can form, so like clouds in their atmosphere. Instead, in these atmospheres, you get things like rocks forming, which I thought was pretty snazzy. But yeah, so then I graduated from Caltech about a month and a half ago, and then I moved down here to start my postdoc, where I'm just going to continue looking at some of these extreme planets, but also some of the stars that host them.
Oh, and I also included the fact that you're a provincial third place medal. Good job, bro. When you were 12, quite impressive.
That was so ridiculous.
Lesson is, I'm the only one who's not athletic.
Just don't brag about it.
Yeah, that's right.
So for the next 10 to 15 minutes, I'll be asking moderated questions, and then the audience can take this time to figure out any questions that you guys want to ask. And then after that, I'll put a QR code up that you guys can scan and ask a question, or you guys can raise your hand if you want to talk directly to the panelists.
You didn't introduce yourself.
Oh, okay. I'm Anishta. I'm a second-year astronomy and astrophysics major, and I do research at the UCSD Stellar Data Lab under Dr. Chris Dyson, who can't be here today, but he's pretty awesome. You guys know him. Yeah, I'm the professional relations chair for SASE, and I'm really excited to host this panel. Okay. Starting the moderated questions. So we'll start with Dr. Keating. So you have a podcast with 330,000 subscribers. It's called Into the Impossible, where you've interviewed Nobel laureates, astronauts, and some of the greatest thinkers alive. So I have to ask you, what's one conversation, if you could choose one, in your podcast that completely changed the way you think of science or the universe itself?
Well, it's hard. I've done 500 plus episodes, and everyone is like my favorite. But just recently, I had an interview with Commander Chris Hadfield, who's also Canadian. He's famous for playing the guitar, playing Major Tom's The Junkie, Space Oddity on the space station to hundreds of millions of views. He's a really cool guy, fighter pilot, astronaut, has accomplished so much in his life, and he's incredibly humble, and he decided after being an astronaut, after learning Russian, after going through all these programs and docking with the space station, living on the space station, that he would become a best-selling fiction writer. And he writes incredible fiction books in the spirit of UCSD non-alumnus Andy Weir, who did not graduate. Unlike Adam, he did not finish his undergraduate. He went on to some success, I would say, The Martian and the new Project Hail Mary. He's been on the show a few times. But that was Andy's whole career, and this is Commander Hadfield's second career. And he's just such an impressive person. We talked about there's a troubling amount of denial about science and misinformation in science and technology. In particular, the most egregious in my mind is the widespread belief that astronauts never walked on the moon. So you guys are rational, smart individuals, but somebody who is not maybe as rational as you guys, named Kim Kardashian, just today claimed that she thinks it's totally ludicrous that people landed on the moon. I mean, just look at the flag. Look at the flag on the moon. It's waving in the breeze. Isn't that stupid? There's no breeze on the moon. Like, nobody thought of that. There are other people that are much more egregious and pernicious, like Candace Owens and other people that spout nonsense, but really try to attempt to deny one of the greatest feats of science, technology, engineering, and math, STEM, in the history of humanity. It might be the greatest achievement so far. I mean, you guys are going to make great accomplishments in space and science and all sorts of cool things. Also, cooperation between different nations. And to deny that is very, very offensive. So along with that, he sort of, convinced me, beyond a shadow of a doubt, how important it is for people that are truly interested in science. You can never rest and say, oh, I just take for granted. Everybody believes the Earth is flat. No, they don't. Or they believe the Earth is flat. Actually, they do. A surprising number of them do. Don't take it for granted. You should know. I always say, I won't do this here, but those of you, I see one of my students from cosmology last year. I always ask, we laugh, oh, these people, they believe the Earth is flat. Isn't that nonsense? But could you prove it? Could you, I'm not going to ask for a show of hands, but do you know how to prove that the Earth is flat? Do you know what to say to these heretics, these people that say such awful things about the United States, about America, about world cooperation, that try to deny our greatest accomplishments? And if you can do that, then also see if you can prove that the Earth goes around the sun, because it's not so obvious that, to a layperson that that's true. So my belief is that you need to communicate to the public what we do. We're privileged to be able to do what we do. Not everyone on Earth has the privileges that we all do and you all do. Take advantage of that and use that to spread the message of scientific fact, truth, and fight disinformation. And that's what resonates recently from the conversation I had 2 weeks ago.
Chris Hadfield is the one who, I think I've seen him on YouTube. He's the one who went to space. He does all those like in-space astronaut stuff.
Yeah, he does like space outreach. It's pretty amazing. But he's just an incredible person. His books are amazing. If you like science fiction, it's what's called hard science fiction. So it's based purely on scientific facts with a couple of details changed around, but like there haven't been murders in space, but this first book is called The Apollo Murders, and this recent book is called Final Orbit, which also involves death and all sorts of hijinks in space, but it's based on historical facts. So it's just amazing that somebody can reach literally the highest heights and then can turn around, not just coming from Canada, up there in the high north, but also can then pivot to do something such a different part of his brain. Reminds me of Adam, who did classes in dance.
You did classes in poetry.
I did poetry, that's right. So he's a really impressive person.
Awesome. I also want to say, if you guys feel the need to use the microphones are there for you. I forgot to say that part. But, okay. Next up, Dr. Burgasser. So, you've spent your career studying one of the most elusive and mysterious objects in the universe. So what first drew you to brown stars, or as you said, failed stars? Brown dwarfs, as you said, failed stars?
Yeah.
And what keeps them so compelling after all these years?
Is it better if I use the microphone to the back?
Yeah.
Okay, great. Thanks for the question. So it's always kind of an interesting process when you become a graduate student and maybe you go into grad school knowing exactly what you want to do, but most times more than not, you go to grad school with kind of maybe a vague idea of what you want to do and you kind of wander your way around. And that was my experience as a grad student. I went up, this was now 1996, and I went up wanting to study high redshift galaxies, so kind of the galaxies that Dr. Nadler simulates. I wanted to kind of study these and look at them through these new infrared telescopes that we were getting at the time. But when I arrived, my kind of promised mentor, my planned mentor, decided to take a year sabbatical in that first year. So I didn't have anyone to work with. And so I started kind of wandering around. And this is actually where having a breadth in your sort of interest helps out. So I went from being a diver here at UC San Diego to being the diving coach at Caltech. Very athletic powerhouse Caltech is. While I was coaching, it turned out that my future mentor would work out at that time. And so, there was a window you could see those people jumping off boards. And then, so I spent about a year kind of wandering around trying different projects and seeing if they were something I liked. I started in physics, I actually went into planetary science because they had the best beer hour on Friday. And as I'm doing this wandering around, I ended up sitting in a talk that was on the types of objects, these brown dwarfs that I study now. And my future advisor was very confused, and the diving coach was at a science talk. It turned out he was looking for someone to work on this new data set that had just come up online to look for these new types of rare objects. And I was desperately looking for a research project to kind of start my dissertation on. And I have been working on that now for 30 years. So sometimes it's just, you happen to be at the right place at the right time and you talk to the right person, and that sets the course of your entire career. So that's kind of how I got started. It's kind of my luck.
Awesome.
Yeah.
I also forgot. Okay, maybe the mic's on. Okay. Thank you. And my next question is for Dr. Nadler. So your journey shows how a non-linear path can lead to pretty amazing science. So I wanted to ask, in your early experiences in tennis or even culinary school, how did that shape the way you approach research today, or did any of that extend to what you do now?
Okay, this is a wonderful question. Yeah, I think it did. So I actually don't think it's a coincidence that there's multiple athletes on this panel. So like a lot of the skills that you learn in other kind of hands-on trades apply really well to research, I think. So for example, work ethic, obviously a big one. I mean, to be good at an applied skill, you have to practice every day, and it's actually not so different with science. In order to be good at coding or to solve physics problems well, it's also just really a matter of practice. The other one is there's a lot of kind of metacognition that goes on in something like sports or even like cooking. You're not only doing things, but you're thinking about how you're doing things and how you're improving or what some areas for growth might be. And it's exactly the same in research. I mean, you have to always be asking yourself, not only do I understand the calculations I'm trying to do, what do I need to learn next, but also like, why am I doing what I'm doing? Am I passionate about it, etc. So yeah, those things definitely informed how I thought about science. And I was also, I think, lucky in a sense that I came to it kind of late, because I didn't really have strong preconceptions about how it worked. I was able to come in as a freshman, like I said, at Santa Barbara, and not really having been exposed to super rigorous or high-level math or science, and just kind of take it at face value and therefore be able to question everything I was learning. And I think that's really important. And we may be in an age where we are losing some of that, especially with proliferation of tools like AI, where we don't have to quite think as much as we used to when we're faced with some new evidence. This also connects to what Brian was saying about being able to actually think through and defend the claims you're making or the knowledge you're gaining. So anyway, those are some things that
Thank you. That's awesome to hear. And then my last moderated question is to Dr. Inglis. So you've combined your past interests in material science and biology, and you're able to combine that with your current career in astronomy. So I wanted to ask, what's the most surprising or beautiful moment you've experienced while observing or analyzing exoplanet data?
In my second year, I was really lucky, and my advisors gave me the chance to work on a new JOST data set. So this is the James Webb Space Telescope, which launched back in my first year of grad school, and it was a time everyone was really excited for the James Webb Space Telescope to launch, because it was expected that it would completely revolutionize our understanding of exoplanet atmospheres, things that we were unable to observe before with existing instruments, like the atmospheres of smaller planets, out into mid-infrared wavelengths, which are unobservable from the ground here on Earth just because of our atmosphere, but the JOST would be able to access these wavelengths for the first time at enough precision to be able to look into the atmospheres of transiting exoplanets, so exoplanets that orbit very close to their host star, and that when we look at them pass between our view and the star, so that's called transit, when the light of the star goes this as the planet's crossing in front of it along the line of sight. And I got to work on one of these data sets. It was mid-infrared data of the planet HD199733b. And this was kind of, other than the phone number name, which probably means nothing to any of you, it's a famous planet called a hot Jupiter. So like I was saying before, if you took Jupiter and put it only a couple of times the size of the star away from the star. So it's basically rolling on the surface of the star, it's so close. And this planet for a long time had kind of been notorious because it was one of the first planets where we made measurements showing that there was really strong winds in the atmosphere of the planet, so 2 km/s winds. And there was early evidence to suggest that there might be some sort of condensate in the atmosphere, so cloud of some kind of rock. So it was NASA kind of nicknamed this the horror slashing planet because it was blowing these shards of glass or rock around at 2 km/s. So a place that you wouldn't really want to be in. But that evidence for the rocks in that planet as atmosphere was kind of controversial because the way the measurement was made was not repeatable, so other people tried to repeat that measurement to see if they could reproduce the result, and they just couldn't. But then when I got to look at this new data from JWST, when I was analyzing it, when I did the first bit and I looked at the data and I saw a dip that was around 8.7 microns, so in the mid-infrared. And we were all like, no, can that be due to some sort of rock scattering feature? So when light hits the atmosphere and there's little rock particles in it, it reflects the light and scatters it. And then sure enough, it ended up being due to these nanometer-sized SiO2 particles, so what you might know as glass or quartz in the atmosphere. So we were able to prove that it was indeed the horror-slashing planet that NASA had claimed it to be a little while before. And that was a pretty exciting moment for me, so one of my favorite results from my thesis.
Awesome, thank you. I think that's good for moderated questions. So I will now open up the audience for an audience Q&A. So you guys can ask anything you want. Either you can raise your hand and ask directly, or if you want to be anonymous, you can also just scan the QR code, put a question, and then I can ask it for you. And if you like a particular question, you can also upvote it if you want it to be answered first, but I'll try to get to everything. And as we wait for them to put in their questions, I will still continue asking questions as they come in. But again, to Dr. Keating, I wanted to ask you another thing. So in your book, Into the Impossible, you emphasize the importance of listening to your critics when you spoke with Adam Rees. But then you followed in the next chapter by saying, to hell with your critics, when speaking with Rainer Weiss. So how did you come to that? And how do you find the right balance between learning from your critics, but also having confidence in your own path?
Excellent question. So I should say that in the course of doing the podcast since 2020, I've interviewed 22 Nobel Prize winners, and Nobel Prize winners are, among physicists, the Kim Kardashians of physics and astronomy, as these incredible scientists were. So the question as to how do you balance these abilities to listen, but also to speak, and those are kind of the two different contrasting emotions that you need to have as a scientist. So I think the most important thing, and I'm curious what the fellow panelists think, is what traits will help you have the resilience through the challenging times as a scientist. No such thing as an easy scientific journey. Nobody gets a PhD unless they do something completely new that no human being's ever done before. That doesn't mean it's impossible. I certainly didn't think I could get a PhD when I would be at the same age as you guys. But for, you have to kind of have the confidence, not arrogance, but the belief in yourself that you can achieve what was by definition impossible before you attempted to do it. So these two scientists that I interviewed, of the 22 that I've interviewed, in the first book, I spoke to these two. So the first one discovered the fact that the universe is not only expanding, but the rate of expansion is increasing. It's accelerating. And this is a phenomenon known as dark energy or the cosmological constant. And it kind of nicely illustrates the two different sides of a scientist's mind that you need to have. And that's because the first person to ever conjecture that there might be a need for dark energy or cosmological constant was none other than Albert Einstein. So Albert Einstein, when he was constructing the general theory of relativity that deals with gravitational physics, he knew that when you observe the universe, that we don't see stars coming towards us and collapsing, and we don't end up in a black hole. They knew about the existence potentially of black holes. So he said there must be something that prevents matter from collapsing in on itself. And he used a term that he called the cosmological constant, or the vacuum term, to inflate the universe against gravity. So it was a form of anti-gravity. He thought it was crazy, but he said this is the only way to explain what I know today. Fast forward 14 years later, I'm Mount Wilson in LA. Anyone from LA? Anyone ever been to Mount Wilson? The shiny dome. You guys have been up there, I'm sure. It's not a big journey from you, from Pasadena. But he went up there, and there's a picture of him talking to Edwin Hubble, after whom the Hubble telescope was named. And Hubble said, I'm sorry, Mr. Einstein, who was later voted the man of the century by Time magazine, one of the most important people in science who ever lived. And he said, you're wrong. And Einstein, to his credit, said, yeah, I was wrong. It was my biggest blunder. Now, fast forward another 70 years, and Adam Rees, who Nisha mentioned, he and his teammates and collaborators proved that Einstein was actually right, but that's kind of immaterial. Einstein was confident enough to propose this thing that was outlandish, but then when shown information that a critic showed him he's wrong, he said, yeah, you're right, I'm wrong. Of course, we should all aspire, to what Einstein did, that our blunders turn out to win Nobel Prizes later on in life. It's too bad Einstein could have had a good career, but for that blunder. So I think that balances that. You need to have that kind of, and another thing that illustrated by Einstein is what Ray Weiss, who just passed away a month ago, MIT, he's the leader of the group that detected gravitational waves. Einstein knew that gravitational waves could be possible, but he said no one will ever detect them. And then literally 100 years later, Ray Weiss and his team, 1,000 people detected gravitational. So the lesson is, Einstein wasn't always Einstein. You don't always have the right answers. You don't need to be an Einstein to make progress, to make a contribution. And you just need to have a nice balance between confidence, but also have humility and be balanced in that way.
Awesome. So I will start asking the Q&A questions and also switch between personal questions. Also in the Q&A, you guys can feel free to put a specific name if you want me to ask a specific panelist. But for the first thing I see right now, and any of you guys can answer, is what skills do you recommend developing your first quarter of freshman year to be prepared for undergraduate research?
Sure, I'll take that on, I guess. So I do take on many undergraduate students in my team. I think I've had now 95 undergraduate students since I came to UCSD in my research group. And that's partly because the nature of my work allows me to work with large teams. So it's easy to kind of have groups of students working on these things. So I think, and I also was an undergrad here at UCSD, and I tried desperately to get research in that first 2 years. And in fact, one of my colleagues I have now as faculty member turned me down. I remember that. But in any case, I think part of it is persistence. So I think you have already experienced at this point, even if this is your first quarter, emailing your professor and never hearing back from them. Raise your hand. That's happened to you? Oh my gosh. Everyone's responding to the students? Wow, okay. Maybe I'm just doing them wrong. So I had many cases when I was a student of, emailing professors looking for research opportunities, no response. And I would just email someone else, or I would email again and just ask. And I would go to, we have colloquia in different departments, and so start showing up there, and people will start to know that, oh, you're someone who's interested in research. So a little persistence. The other thing is, I often will get students who think they know exactly what they want to do in that first quarter, right? I came to UCSD because I'm going to be the next Einstein or the next Ray Weiss, right? So, and it's important at this stage to really have some flexibility and try different things. So when I came to UCSD, keep in mind I'm an astrophysicist, my first quarter I was a classical studies major. Because I thought the best thing I want to do is just read Latin for the rest of my life. And I took one class in that, and I was like, I definitely don't want to do this. So then I was a theater major for a little while, and then I was a cognitive science major. And it took me until about my junior year to like, actually, I do like math and physics, and maybe I'll just stick with that. And so it seems like I went down a lot of, dead ends, but actually, all of those experiences have been enriching for me to this day. So being a theater major, I learned to speak in front of people in a way that doesn't make me cower, right? So I do this all the time with teaching, but it was actually helpful to have that experience as a theater major for a little while. As a classical studies major, I love to read, and all I do is read. In fact, the reason I dropped classical studies is I didn't want to write. I thought, oh, I'm going to do something physics where I don't have to write anymore. Guess what? That's all we do. That's all we do. We write all the time. So having those skills that are beyond what you think is kind of the straight and narrow path for that research is really important. So being open to kind of how these different skills come in, but also being open to like, maybe I don't want to be an astro major, maybe I want to be a data science major, but I'll try some astro thing to learn about data science, or vice versa. It's good to kind of try these different experiences out, especially at this stage in your careers, because it's actually harder to do it later on, except with your Dr. Nadler. It's good to kind of get out there and try these different things so you can really build that tool set, and you'll find it applies in very unique ways. And I think you said kind of a lot about that in terms of your experience with tennis and teaching that.
Actually, follow up for maybe both of you guys that what would you say to students who feel like they're behind or they don't know what, like if they're in the right major, they're worried that they're starting late?
Sure. So, I mean, I just want to echo one thing that Dr. Burgasser said, which is like breadth of knowledge is so important these days, and I feel like it's a skill that's or an attribute that is also being lost with some of the other things I was mentioning earlier. And so, I think to your question, what I would do is reframe it, right? If you're feeling behind, maybe the question you should be asking is, what do I really want to be learning? Am I learning? Am I challenging myself, right? And you may or may not be behind. It's actually quite okay to be behind sometimes. In fact, we probably all feel behind every day as in our kind of working lives as scientists. But I suspect for all of us that's because we're trying to really get to the bottom of something, right? Or push ourselves in new ways. So keeping that in mind is important, and I think learning broadly is really key for research.
Okay, this next anonymous question actually kind of, it intertwines with that, so it might be the same answer, but it's basically, should students pursue interdisciplinary experiences outside astrophysics to strengthen their research and perspective, and what experiences are most valuable?
Yeah, I can just say one brief thing, and then I'll pass it along. So one of the reasons I was drawn to what I study is exactly because of this, because it's a very interdisciplinary subject, and that's actually what I find most rewarding about it. So when we study something like dark matter, we have to know a lot of things, right? We have to think about how galaxies form, which is a very old astrophysical problem. We have to think about particle physics of dark matter, so we need training in like theoretical physics. We have to think about computation, right? So data science, machine learning, writing programs at scale to actually do the simulations. And that aspect of like different fields coming together is what I find the most exciting, because then I get to go learn from other people when I go to conferences and I have a conversation with someone who is working on particle dark matter physics. I actually have a chance to learn something new and then import that into my own research. So that ability to have conversations with people, no matter what they're studying, whether it's even within STEM or not, is really incredibly valuable.
So one of my undergraduate researchers is in the audience right now. I won't embarrass him, but he has this exceptional ability to take diverse skills from everything from 3D printing to knowledge of AI to generation of web technology to understanding astrophysical polarization to the needs of a data analysis person to somebody that does hardware, and that speaks to what Adam, Professor Burgasser has said. The breadth of knowledge, and also even said as well, that having breadth is really important. And one thing I echo to outside of just research And I told Nishta this is how we met. You know, she was interested in, curious about YouTube and how do you get involved in YouTube is like nothing, nothing like anything I do for my day job of teaching and research and travel and speak. But it has all these micro skills. Like there's no such thing as being a professor. There's no one skill set. Nobody ever tells you what you need to know for everything. There's too much you need to know. So too for understanding YouTube. But I told Nishta, you can correct me if I'm wrong, but by doing something, just doing it, even if you never release it, I think like explaining what you're curious about, what keeps you up at night, what you talk to your friends about, what other people tell you you're a nerd about, leaning into that, and actually just creating based on the pure love of it, not for getting, virality on TikTok or whatever, or getting likes and so forth, as my daughters always want to kind of point out. That seems to be a huge thing for them. But in reality, there are all these micro skills from, how do you package something, and how do you put a thumbnail, and how do you take an image, and what's curious, and what do people want to know about? And the best advice I've given, because I've learned it, is, explain things to the you of 2 or 3 years ago. What piece of advice would you give to your younger self, younger brother, younger sister, whatever, but what would you tell yourself in order to give them the confidence to do as you've done, which is to go and do these challenging things? And I think it's a series of micro skills that when you add them all up, they become this supermassive black hole of abilities that then, then you can say, well, this could be useful in my career, or my research, and so on.
I also specifically want to add, so I do a lot of art outside of science. I spend a lot of time painting and doing digital art. And I also read and have done a bit of writing in my life. And all of these things, like creativity in general, the ability to take a blank page and make something out of it, or think of something that doesn't exist currently. Creativity is a very important part of being a scientist and being able to think in ways that no one else has thought about. So anything that kind of fosters creativity, like whether it's writing, reading, all of that is very important. And also it helps you learn how to present what you want to tell everyone. So your science doesn't mean anything if you can't communicate it to other people or make ways to show it to them. And creativity and art is very important for that.
Thank you. Our next question, and anyone can answer this again, is what are your thoughts on 3i Atlas and what sort of new breakthroughs are expected from this?
Speaking of someone who just did a YouTube video that's been seen over 100,000 times since last night with Avi Loeb. Avi Loeb is this character, professor, author, one of the renowned astronomers in terms of how much he's published, and he kind of brought a lot of attention to this object 3i Atlas, which most people, I would say, you guys are much more expert in these things than I am, but most people seem to believe is a comet. And it was funny to see, I kind of posted that I was going to do this with him on Twitter and Instagram, and then Brian Cox, who's much more famous Brian, he's my son's favorite Brian astronomer, which is kind of upsetting to me. There's Brian Green, at least I'm better than him. But he said this is nonsense. Everyone's saying it's an interstellar, technology, or it's debris, a garbage barge, or it's some alien mothership that's going to release. Right now, it's at perihelion, which is the closest approach to the sun. And Avi's been saying, things could happen if that's true. He was on Joe Rogan earlier this week, which got almost as many views as he got a lot of views with Joe Rogan. But he's been making a lot of attention about this. I think the jury is certainly more in favor of it being a natural origin, but it is unusual. And I think what's interesting is to see kind of the professional, kind of approach to it. And then there are people like David Keating, who's a friend, who's been to visit UCSD, and we've talked a lot together. Who takes a very measured approach. He's not going to criticize somebody. He's not going to sling arrows at him, versus like Brian Cox saying, this is idiot, if you believe it's aliens, you're stupid. And so I just think it's interesting to see the different personalities in science, and we really do need all different perspectives on it. But I think, in the final analysis, it's a very interesting, curious object. It definitely came from another solar system. I think that's clear. What it's, what's inside of it, does it have intention? I don't know about that, but it's gotten a lot of attention, which I think is net good for astronomy and for understanding more and spreading interest of what we do to the public. Because if the public loses interest in what we do as astronomers, as physicists, kind of that could be the end of what we do, because we only serve because they support support us via their tax dollars and your tuition payments and so forth. Study these things.
So it's funny, this morning at like 8:30, I was on the radio station talking to someone about exactly this issue. It was exactly about, so, aliens? Are we made aliens? I didn't have quite the same viewer coverage for that. But I very much agree with Brian in the sense that it's important that as scientists, we are both critical and also open-minded, because we are always finding that some of our assumptions or some of our well-trodden kind of beliefs can be overturned when we sort of look into the evidence. And I am very much on the side that this is a comet. It's a natural object. It's come from another solar system. We've already seen 2 other ones. Like that's the simplest kind of explanation. And it's also, I think we talked a little bit about this, but critics, right? Like it's important, I think, for someone like Avi to hold on to his beliefs while also acknowledging, that there are other explanations. And despite kind of I think a lot of the sort of press around it, I think Avi does see that, right? So he's still pushing his idea, but also understanding what the critics' perspectives are. And I think it's an important lesson for all of us, right? And so, I would say, again, my personal, given kind of the evidence we have so far and the kind of most obvious explanation for this thing, I'm not going to go into the bomb shelter quite yet. But it's important that we use those criticisms and we use those outside ideas to essentially strengthen our understanding. Whatever side you are on these kind of debates, right? Like, if we can't say, I can disprove, your sort of idea, then we have to take it seriously, because, or we have to figure out a way how we can disprove it, and that's how science moves. We don't just shut down ideas because we don't like them. We have to really look at the evidence, we have to really put in predictions, we have to really test them, and then we can start to say something more cogent about what these kind of ideas are. So, it's it is fun because it's, people are really excited about, this thing from outer space. There's a lot of great science on it. There's 80 publications on this object since it first appeared back in January. And that's a beautiful body of work, and it's also fun to talk about. So there's all different sides of these
And
things.
reminder, and it reminds me to remind you that afterwards you can come up and get a real fragment of a known meteorite, which is an asteroid, that fell to the Earth. Come up here and join my YouTube channel and my mailing list, and you too will get a fragment of the primordial solar system that looks a lot like what Atlas might look like, or at least Oumuamua might look like.
And how old is it again?
It's at least 4.3 billion years old. It was found in Argentina. It's made of composition that has a lot of heavy metals. It's highly magnetic, extremely radioactive. No, it says very slightly radioactive, but yeah, you can play around with it, do some experiments with it, and it's very dense for its given its appearance. It's a metallic meteorite. There are other types of meteorites, but this one is the one that I have. And yeah, so come up afterwards and grab one.
Thank you. Another question is, for those that run simulations, how do you balance computational efficiency with accuracy and detail?
Yep, wonderful question again. So there's actually a lot that goes into designing simulations for astrophysics or cosmology, and it's very interesting because different groups, different researchers out there take very different approaches to this problem. So, for example, when we try to simulate a galaxy, we're essentially faced with the problem of scale. So galaxies, for example, a galaxy like the Milky Way, its size is an astronomical unit we call kiloparsecs. It's maybe like 10 kiloparsecs wide, which is many millions of light years. But the point is that the individual stars that form inside of that galaxy, those form on scales that are maybe 1 million the size of the entire galaxy, or much smaller. So some people try to simulate the physics of the formation of individual stars, but we could never, given our current computational resources, actually put that physics into a full-scale simulation of the entire galaxy. So we're immediately faced with this problem, and it's actually pervasive in all of astrophysics, essentially, which is there's too big of a range of scales to simulate. We can never actually simulate the full universe. So we have to start making choices right away.
one thing that we might think about in the context of this Milky Way simulation is, okay, do we actually need to simulate the formation of every single star in order to address the scientific questions that we are interested in? Maybe we just want to know, hey, what's the total mass of stars in the Milky Way? In which case, we don't need every single one. We can do some kind of averaging over patches of different stars. So that's just one example of a very general set of techniques that we develop, which is basically a set of physical approximations to capture the aspects of the systems that we care about in a controlled way, so that we won't make mistakes for the actual answers. So this type of thinking about like algorithmic design and how to actually set up the simulations in a way that's effective to get at the questions we want to is basically half the battle, and the other half of the battle is implementing this in code. And so I think there was an earlier question about research skills. I mean, a huge and important one these days is the ability to work numerically and actually implement things in code. Python is a great language to start with, and if you go down the kind of simulation route, then you'll slowly drift towards languages like C or C++. And that's super important no matter what you're doing, whether you're the one running the simulation or just analyzing the outputs of the simulation. At the end of the day, you have to work with the data numerically because the problems we're solving are just too hard to write down on pen and paper and actually solve mathematically. So it's actually driving a lot of work. And one more thing to say about it is there's really exciting advances in this field with the advent of, for example, GPU accelerated computing and also AI. So our codes are becoming written more efficiently by certain AI tools, and we're able to run the simulations in kind of a bigger and better way. I think there was one a couple of days ago that ran on something like 4 million computers that were like distributed throughout the world. So it was one of the largest simulations that was ever run. But even in that case, they weren't kind of even close to the level we need to be to actually capture everything. Yeah. So those are some practical examples of simulations.
Thank you, Dr. Nadler. And I had a specific question for Dr. Inglis. So, given that you were an undergrad, like many of us not too long ago, what's one thing you wish you'd known as a student starting out in research?
Oh, that's a very good question. Well, I guess for me personally, something I've always struggled with is being willing to ask for help when I get stuck. Because I always kind of had this mindset, especially when I was doing a physics degree later in undergrad, that asking for help meant that I wasn't smart enough to be here and that I was an imposter and that it would somehow, everyone would start judging me if I went up to someone and said, hey, admitted, hey, I'm stuck, what should I do from now? And I wish I had overcome that a lot sooner. Then probably still have not overcome it entirely, because it's just kind of the thing you carry with you when you're a woman in STEM these days. But yeah, learning to ask for help, learning to admit when you're stuck, and to embrace the fact that none of us really know what we're doing. Like half of science is just educated guesswork and trying to something to see if it works, and then you fail a lot, and you don't always know why you fail. And that's honestly part of the beauty of science is we try a bunch of things and maybe 1 out of 100 work, and then you find something really cool. So yeah, so that's probably something that I wish I had known back then.
That's actually very reassuring. And then there's an anonymous question for Dr. Brian Keating. How can we develop our scientific communication skills, and how can we get into science communication as a career? And they loved your World Institute lecture.
Oh wow, that was a couple of years. That was a great thrill because the way that science used to be done, it wasn't with papers and Nature magazine or where Kim Kardashian publishes in People magazine. It was, you would just go out in front of a live audience and you do your reaction, do your experiment, take your frog out and electrocute it and whatever with meteorites and magnetic fields, and that's what they would do. And if you got it wrong, as Dr. Inglis just said, 99% of the time, imagine how embarrassed you feel up on stage with like 400 people on a London evening. That was a great evening for me. 2 of my 5 kids were there, and it was a great night. Thank you for that. So the lesson that I tell everybody, including you so she can acknowledge this, is make 100 crappy videos, get them all out of your system, get the practice, learn how to use a camera, learn how to speak on confidence, learn how to write a script, again, there's so many tools that didn't even exist when I started 5 years ago, and I started super late, but the best time to start is 10 years ago, and the second best time is today. So get started. Your first 100 videos are gonna suck, and no matter what, but you're gonna learn all these micro skills, and if you improve 1% per day, then the rule of 72, which the economists tell us, you'll double incredibly rapidly. You'll make progress so fast that in a year you'll be 37 times better, or whatever it works out to be. So the key is just keep doing it. Don't give up. Don't think that anybody cares about what you're doing in the beginning. I mean, some of my original or early videos have 10 views or something like that, and I was happy. Oh, I got 10 subscribers, in a month. Don't do it for the metrics. Just do it. Practice. Learn what works. Learn from other people, and don't be afraid to ask for help as well. And yeah, you'll definitely feel things. I mean, I've had things. People tell me, oh, your hair is awful, or they say really. I mean, on the internet, nobody knows that you're a troll. But then sometimes you hear wonderful things like, you made me want to get into science. My daughter is now, she's a junior at Cal Poly Pomona. Someone just told me. It's incredible. So you never know what it will lead to, but you got to get started. And don't think that people care about what you're doing. They don't. They care about themselves. I mean, think about it. Are you thinking about what your friend is doing? She's making a video. No, whatever. You got your own things to worry about. So just get started, make 100 videos, and then don't forget about me when you have more subscribers than me.
Thank you. So just letting you know, it's almost 7.
Oh.
It's 6:56. I think this is one last question we can get to before we can get food. So what are your least favorite parts of physics? Mine is E&M, and I'm wondering if you guys like everything or also have a weakness.
I hated stat mech. I still do. Not my favorite class.
I hated group theory. Exactly. What is it? Who cares? I hated it.
I probably shouldn't admit this, but for me, optics. This is ironic because I do, just like studying gravitational lensing, but the reason is I just always found it super counterintuitive, and I didn't like that about it. Like, it's very hard to visualize solutions in optics.
I don't have a least favorite part of physics because there's too many things to me. I actually want to ask a question. So what kinds of things are you, if you're not a first year because you're still kind of learning the ropes and stuff here, but maybe you're a second year and above, what kinds of ways have you been maybe disappointed or surprised? What ways has UCSD maybe not lived up to what you wanted? I'll give you an example. I asked a lot of my students, and many of my students, or some of my students are here, former students, what are your professors' attitudes towards using AI in your class? And a lot of them say it's forbidden. I was just at Princeton on Tuesday visiting some friends. They're like, we don't let them use anything, and even the professors don't know how to use it. So as an example, maybe you don't have to answer now, but people can submit what their things are. What are you maybe surprised about is a different thing? I mean, you mentioned a lot of questions about, how do we get into research, how do we succeed, what are the challenges? But what sorts of other things did you have expectation that UCSD would be one of the best institutions in the world? And we want to understand, selfishly want to understand, how are we not living up, or how can we do better to prepare you for your future, which again, nobody really knows the future, but what are you hoping to get out of the remaining time that you have here, and what have you been surprised about? Selfishly.
I wish physics did more demos and visualizations. I think there's a lot of it's unavoidable that you're gonna run into math and physics, but I think there's you can also demonstrate why you're even doing it in the first place with a really good visualization. I had I think in high school, my physics teacher did a really good job of doing demos and showing why we were even doing it in the first place, which hasn't really happened in physics here so far, which might be a funding issue, I don't know, but
No, we have a huge demo. So actually, I try to do a demo every day, even in cosmology.
Okay, yeah.
No, it's a great
Yeah.
point. Yeah.
I'm not going to name which classes, but some classes there's, I think a big part of physics is building a very good physical intuition for things, and I really like math, but there's some points where it's oh, I can see the math, more physical examples of like, oh yeah, this is what humans do.
Mhm.
It's really cool because it looks like this.
Any other things, you guys? Or you can also submit it to me so she can read it to us anonymously. You don't have to worry about repercussions. They won't be that bad. They won't be that severe. Already admitted here. Okay. Good.
I guess I'm saying when I started research, I guess this was my mistake, but I did expect to be kind of handheld through it. I was like, oh, so what do I do next? What is this thing? What is this thing? And then I realized that my professor actually is mentoring and teaching a lot of other kids, so I have to figure out a lot of this stuff on my own. And in a way, it's good because research is going to end up like that. You learn things on your own. You don't have particular, like, in my research group, no one's doing the same thing, so I have to figure it out. And I think that's actually, it's the hardest part, but it's probably the best part about research. Okay, it's 7 p.m., so you guys can actually get up and go get some Mendocino Farms. Just make sure you scan the QR code before you have to show them that you scan the QR code before you get food. This is how we get funding.
Come up here, get a meteorite, but you have to scan the QR code on the card before you get your meteorite. So I make sure, Okay?
Oh wait, okay. So sorry, let's keep that. Wait, before, actually, I'm so sorry. We have to do a media thing really quickly, so if I could sit down and then, yeah, let's take a video for Instagram.
That never happened.
Okay, does everyone want to sit in the front? It would be easier.
We pack it up close to the front, thank you.
Oh, yeah.